Hello, everybody. Hi. This lecture in particular was a lot of work for me to prepare because I many times know how to explain things sort of in a simple manner and then go to more complex. But this is a field in which the language is terrible because it makes contact so much with condensed matter. It's very heavy. Condensed matter, properties of materials is a lot of things that particle physicists actually are not very trained on. And so I wanted some very simple examples that I am going to give to on the blackboard. I tried writing on my tablet and posted in that way. It was so bad that I'm going to use this. But at the same time, I mean, when I get there, right? And I prepare, you see, a set of slides. I'm not sure it will be as long as an hour and a half. We'll see. And then we chat if I finish early. Okay. So this is my last lecture, and I will develop try to explain this direct detection of light dark matter. As I explained already before, right? The difference between WIMPs and light dark matter is sort of recent. Actually, before WIMPs could be lighter too, you know. But the issue is that when there were dedicated searches for sub-GeV, which was also how people say sub-GeV WIMPs, instead of saying sub-GeV WIMPs, but it could be a little bit below GeV, it is really that they are not above threshold in the traditional WIMP detectors that have been optimized in order to detect WIMPs. In order not to have to say all that, then the language developed into creating a word that means all of this. Well, WIMPs still could be weakly interacting, or there are many other type of candidates, could be much weaker than weak. But in any case, light dark matter means that you have to detect them in other ways, which is not the scattering of nuclei, typically. Although I will mention that is also a search for, but in excitations, in coherent excitations. Okay. So I went through this already, I think, in lecture 2, that the maximum energy, if you have particles that are below a GeV, you don't reach the KV threshold. The maximum energy is given by the reduced mass. And this is a particular example when the particle is much lighter than the nucleus, big M is the mass of the nucleus, then the reduced mass becomes the mass of the particle. And here you can see then a simple relation with the mass of the particle in which mu has become the mass. And so typically it's electron volts, tens of electron volts, what you deposit. And although you cannot deposit enough energy in the usual sense, coherent elastic scattering, it could deposit enough energy, 1 to 10 electron volts, in interaction with electrons. And this is what we are going to cover, how not only interaction with electrons, but also other ways, dissociation and then coherent interactions. And there have been many ideas, and I will mention several of them, from using superconductors, semiconductors mostly, etc. Superfluid, I will mention. All right, so let us see how this energy matching of energy targets. The nuclear size is well matched for the nuclear size and mass. The momentum exchange is essentially the de Broglie of the incoming particle, is of the same order of magnitude. is well matched to the atomic size and to the atomic mass. So if you have 2 billiard balls, right, one could, in principle, even communicate all its kinetic energy to the other. You have done that in physics 1, whatever the equivalent was. But instead, if you have something that is much smaller, and that much smaller would mean that you have, for example, typical of the atomic size, the atomic size in distance it corresponds to the inverse of 12 GeV. The inverse size of a nucleus corresponds to, oh wow, here I didn't put it correspond to GeVs. There's something here missing, I'm sorry, GeVs. This is a reproduction of something that I said already, but there is something, there is the units are missing. A Fermi is 1/200 MeVs. So essentially it is 1/200 MeVs. So this is in GeVs, inverse of GeVs. So the energy. MeV, yes, 200 MeV, probably 100. Yeah, here there has to be some MEVs, could be MEVs actually, divided by 8 to the 1/3, something like this. Yes, Fermi is 1/2. I always remember it's 180 or something like this, MEVs. So there is an MEV missing. So the energy to be deposited in a dark matter collision is a fraction of the initial dark matter energy. So here it is, for example, the kinetic energy, the characteristic velocity of dark matter passing through a detector is 10 to the minus 3 C. C is 1 here. So the kinetic energy is 10 to the minus 6. And the momentum transfer is 10 to the minus, I was very tired yesterday night when I wrote this, 10 to the minus 3. 10 to the minus 3 times the mass is the velocity times the mass. This is the typical de Broglie wavelength. I will correct this before the lecture is posted. And so WIMPs that have masses larger than a GeV have characteristic momentum transfers that are in the MEVs, and they interact with single nuclei. So you can forget about all the rest because it interacts essentially with single nuclei. It doesn't see anything else besides a single nuclei. Instead, like dark matter, with the mass in the range MEV to GeV, Q in the range of keV to MEV, start seeing the whole atom. And so you have an atomic excitation, typically an electron excitation that changes your atoms. Lighter particles have even a smaller momentum transfer, or if you want to talk in terms of the Broglie wavelength, includes many, many atoms. And therefore, what you excite, what you interact with, are not individual atoms that the particle doesn't even see, but collective atomic excitations. It could be a different type of excitations. Phonons typically could be magnons if this is coupled to spin. Magnons are waves in a spin. So this is for spin-dependent interactions. So this, I stole this. I told you I steal the slides, but I give credit. And Ruben Essig always has fantastic slides, actually. So I end up stealing quite a bit of things from him and giving him credit, actually, I always give him credit. In any case, so here you can see, this would be, with some uncertainty, the elastic non-relativistic interaction, typical non-relativistic elastic nuclear interactions, recoils. You see that it is very ineffective in order to detect anything that has, this is for scattering, a mass which is below an MeV. But the maximum energy to be deposited is the kinetic energy. And so this is the kinetic energy. Of course, the expected energy would be a little lower, but still it will be a fraction if you find the proper way of communicating it. essentially, this light particle sees a nucleus as a wall, right? You are trying to push a wall by throwing a ping pong ball to it. It doesn't do anything to the wall. So you have to find another ping pong ball to actually collide with. But the things are much different because these ping pong balls now are included in a medium, and therefore you have to consider all the difficulties that that entitles. So in any case, so here is what you gain roughly. And therefore, depending on the type of mass and kinetic energy that you have, then you would move down here, passing from, if you deposit energies that are of tens of electron volts, then you can have xenon and argon, for example, and also helium. So these are novel liquids. And this has been already done, actually, by xenon, for example. Then if you go to the order of 1 electron volts, then you go to semiconductors or other type of detectors, typical energy. Then 10 to 100 milli-electron volts, you go to this polar materials or Dirac materials. And then, well, if you want to go this low, this is much more complicated. There are some protons and stuff in superfluid helium, in semi-metals, etc. It would be very difficult to reach to this point, actually. And so here I mentioned that this is for this band, is for nuclear recoil, but there are many other effects, and I mentioned a few of them. Dark matter electron scattering in different ways, dark matter nuclear scatterings with a Migdal effect, which produces also an extra electron or photon, or collective modes, magnons, or phonons and magnons. Please interrupt me if I say anything that, yes. Yes, the threshold, namely, if the available energy that you have, namely the kinetic energy, you cannot give more than the kinetic energy in a collision. So this is a rough classification of the type of materials. You have to do something in the material. If you don't have a particular excitation that will be available to you, namely, if your energy is not above threshold to produce something in the material, you're not going to measure it. Now, what do you produce? What do you produce depends on what this your particle is interacting with. And I told you, it could be, if it is heavy enough, the energy is enough, the momentum is enough, 1/q is enough to kick a nucleus. And then you have a dominant elastic interaction with nucleus. Otherwise, you don't see the nucleus now. You see the whole atom, and the energy is smaller. The momentum is smaller, 1/q is larger. Or you see many atoms, and therefore the excitation that you can do is coherent excitations okay. This is a rough classification of the physics. It's correct. It is a correct way of thinking of the type of materials that you need. Now, this is a way of classifying. It's very similar. This will be the nuclear recoil. This is, well, I've already computed this. This is the maximum nuclear recoil for a nucleus of mass m. This is the reduced mass between the dark matter and the nucleus. It's much smaller than the kinetic energy of the particle m chi. It's the particle many times. Either I use little m or m sub chi. But then you can produce, here I'm going to roughly talk about electron recoils and phonons. Phonons, this comes, by the way, many of the things I'm going to say And also for the references. The references are a huge amount of references. So I'm going to direct you mostly to two things. One review in which Jure here is one of the authors, recent review that I mentioned several times already. And these lectures of Tongyan Lin that I have found particularly useful. And they have also, these are TASI lectures, which are equivalent to this. TASI are a bit longer, but usually they are 5 hours of lectures or something like that one gives. And she has done a fantastic job. This was a few years back, explaining. And the simple examples come from there. They are much better explained there and in that source. And this picture comes from her. So the atomic ionization in fluid is the binding energy. The threshold for that is the binding energy of the outer electrons. For example, it's 12 electron volts in xenon, the outer electrons. The electron excitation in semiconductors, the excitation that you use is for electrons to go from the valence band to the conduction band. And this jump is about of the size of electron volts. So a few electron volts. And in superconductors and in Dirac materials, I will explain what these are, like graphene, is the gaps can be much smaller, milli-electron volts. However, these are designed materials. They are difficult to fabricate, and there's not a lot of them. It is very costly to fabricate it and to use enough of it to use for detection, to make a detector. Phonons, magnons cut off at milli-electron volts here, because essentially the calculations have been done only for sub-MeV dark matter, and this is the energy. Phonons are not really used. Well, they are very important during the detection. It's not in the interaction, but in the detection, all the complications of the materials have to be taken into account. So it enters into the performance of each material. So, but not in the as a main form of coupling, the dark matter coupling in the detector. All right, so let us start with the kinematics of dark matter scattering in on bound electrons. The kinematics is very, yeah.
By now, I think dark does go above a milli. I think so. I might be wrong, but I think more recently people have found these connections to the dielectric function that allow it to go above as well. I think again, I'm not
with phonons and magnons.
It's phonons. I think the dark L works.
The cutoff, I intended to say lowest.
Yeah, okay. So
not up. I'm sorry, I didn't explain. How low you can get with this kind of thing is milli-electron volts. It will be. I mean, I don't think you can go much lower.
Oh yeah, it's just no sense that it can be below.
That's what I meant. The cutoff in going low, not in the lower limit. Let us say you're right, but it is yeah. It's maybe it's not well written here. Okay, so this is the an excitation. So the dark matter interacts with the electron, and either ionizes an atom, and this is what could happen in a fluid, for example, liquid xenon. The atoms are almost free, so it could be you could see atoms being ionized. But if that happens within material, in a crystal, for example, then you do not ionize. I mean, in the material, the electrons are in wave functions states that are associated with the whole material. So actually you are changing from one state in the material to another. But in both of them, the kinematics is very different because you don't have conservation of momentum. These are not free particles. When you have the electron, in this case, is bound to the nucleus, and therefore there is no translation line invariance unless you make the assumption of free particles that you can make with some educated guesses just to get order of magnitudes, as physicists always do, back of an envelope order of magnitude calculations that are approximately correct. And if you get the order of magnitudes right, then you do the proper calculation, right? We always do the same thing. We convinced ourselves going through something. So here it is that actually, so you start with a certain momentum. The dark matter particle is free. So it's free at the beginning, it's free at the end, and therefore it has definite momentum. So the momentum, the initial momentum is P. It's the mass times the velocity. They are non-relativistic. And so the final momentum is P minus Q. Q is the momentum transfer, is whatever it has transferred to the material. So these two are perfectly, the energy and the incoming and outgoing dark matter particle momenta are perfectly well defined. And then you have to compute the energy deposited by subtracting the initial minus the final. This is the energy that was deposited. For the scatterings of a nucleus initially at rest, of course, and we have a practical rest, the kinetic energy of nuclei in detectors, and they are cryogenic, they are at very low temperatures too. So actually it's not a bad approximation. Then the energy deposition is equal to the recoil energy. And so energy conservation implies precisely this relation, and you get then therefore what we use usually in the calculation for the recoil energy. Now bound electrons have a size, a typical size, which is of the order of the Bohr radius. The Bohr radius is the inverse of alpha and the mass of the electron. Namely, it is associated with a typical momentum for the electron, which is the inverse, which is alpha me. And namely, the velocity, typical velocity of a bound electron is of order alpha. Alpha is, order 10 to the minus 2. And therefore, they are moving faster, typically, than the dark matter, which has velocities of order 10 to the minus 3. And of course, the initial and the final wave functions are different. And that's a complication that you have to take into account. Now, the kinematics, therefore, is more complex, as I said. So this is what I just mentioned. And so there is energy conservation, but not momentum conservation. Now, energy conservation you can use, here it is, but you have a complicated function. This is the energy relation depends on the dispersion relation. The energy as function of K is different within different materials, and it doesn't correspond. It's not the one for free particles. And the same thing for the final state. It could, if this is a ionization, then yes, this energy is then K prime square over twice the mass, because it's for a free particle. But otherwise, it will be whatever it is within the material. Now, there is a useful toy model And this comes from Tongyan Lin. Again, all my very simple examples come from her. That's a great way of introducing things, doing toy calculations that you can actually compute. And then you can see the final result for full complication, and sort of understand how what the different elements that enter into the final correct equation come from. Because you guide your intuition with models that are simple. And so here it is. A useful toy model is a scattering of a free electron with initial velocity alpha. So you assume that actually your electron is free, but it has the velocity or the momentum that would correspond to typical momentum of a bound electron. Then you can use energy conservation, where mu now is here, this mu that appears is the dark matter electron reduced mass. And then since the velocity of the initial velocity of the electron, as I said, is about 10 times, 1 order of magnitude larger than the initial velocity, which is k over me, is larger than p over m chi. K is the initial momentum of the bound electron. P is the initial momentum in my notation of the incoming dark matter particle. Then we drop this left-hand side, because you see P, here you have P over m chi, and here you have K over m. So you actually say that this is, the left-hand side is much smaller, it's negligible, so it's of order 10 to the minus 1 of the rest. And therefore I take these two to be equal, these two terms to be equal to each other. This is what is here. And then I write Q, you see Q here. Here I have Q squared, here I have Q. Then Q is of order mu, the reduced mass divided by Q is approximate. Well, in the two regimes, if the mass of chi is small enough, these are practically similar, me and mu. In any case, here I have Q is mu mb. Okay, so this is these are all the approximations in this toy model. And now you estimate this, you make, this is algebra. At this point, this is algebra. And I'm not going to prove this, but actually if you go to Tongyan Lin's, you can see a better proof. But this is what you get in the limit in which the mass is much larger, the mass of the dark matter particle is much larger than the electron. In this case, what you get is that the energy deposited becomes a few electron volts independently of the mass. You see that it becomes equal to the mass of the electron, the velocity of the electron, and the velocity of the, or speeds, because at this point is a speed of the incoming particle, or the momentum of the electron times the velocity of the incoming particle. This is the order of magnitude, becomes a few electron volts independent of the mass. Of course, this is a typical value, a few electron volts. As I mentioned, higher is also possible because the momentum is, the momentum peaks, the distribution peaks. In fact, I'm going to now start using the blackboard, peaks at the inverse of the Bohr radius, but of course it could be much smaller or much bigger, the momentum of the electron inside the atom. And so for xenon, the outer electron is 12 electron volts, and that's so this is just an estimate. On the other hand, if the mass is the mass of the dark matter particle is very light, it's much lighter than the mass of the electron, lighter than half an MeV, therefore, the mass of the electron, then you get that omega can be the whole kinetic energy. So you can communicate the whole kinetic energy of the incoming dark matter particle can go, all of it. And moreover, in order to get a positive energy, otherwise you get a negative energy, there is some restriction in the momentum of the particle. But in any case, this is what is shown. If you see here, this is the electron recoils in this simple example at the MeV, when the particle mass becomes equal to the mass of the electron, which is half an MeV, you get to you separate the two regimes, one in which the whole of the kinetic energy can be communicated, and then the other in which it becomes a constant, the maximum becomes a constant. Let me see. Okay. Instead, in this review, actually, you see Cirelli, Strumia, and Supan here. Very nice review, a lot of work. I use many of his, I think it is the second or third picture that I took from them. But you see, we are still each other. I think we all do the same thing because there are, you stole this from her. Well, yeah, you see that once somebody actually comes up with a beautiful picture, you have to use it because we are visual people, right? We communicate a lot visually. And so good diagrams go a long way. In any case, so you have here that actually there is a general kinematical property in which the upper limit on the I call omega the energy deposited in the material is bounded from above by this parabola, digamos, let us say. This is a deformed parabola because this is a log. Parabolas don't look very well in log. They look weird. So here you have for different masses what you reach, and you can deposit energy below here. So this is the energy deposited, and you can deposit energy here below. So here you have atomic and molecular levels, semiconductor levels, and here superconductors, Dirac materials, etc. Again, another way of seeing what are your possible targets. Okay, in superconductors and in Dirac materials, both you may reach the lowest you may reach is milli-electron volts, typically milli-electron volts. However, Dirac materials are much better than superconductors in some respects, and this is what I wanted to mention. In superconductors, you know that you produce copper pairs, right? Or the electrons that are close to the Fermi level pair up, and so they produce two electrons, bound states of two electrons that are bosonic, and this produces superconductivity. The breaking energy, the binding energy of these Cooper pairs is milli-electron volts, and this is where this sensitivity to milli-electron volts comes from. Problem is that if you are within the Fermi level and you gain 1 milli-electron volts, your electron is still blocked because the Fermi, below the Fermi level, all the states are full. And so it cannot go. So essentially, in these materials, you have only available to excite only the Cooper pairs that have energies within milli-electron volts of the, it's, here I wrote the energy of the Fermi level is about 10 electron volts. It's huge with respect to milli electron volts. And so you can access only the little layer of the excitations that are very close to within 1 milli electron volt of the Fermi surface. So the amount of target that you have in your material is considerably reduced. Also, typical computations for this type of so you always think of benchmark models that allow you to compute something that would make sense, just to get an idea of how good it would be. So I mentioned that dark photons mix with the usual electromagnetic photon. And so it interacts through this mixing, it interacts electromagnetically. And the problem is that in superconductors, there are large polarization tensors that appear. So the effect, the medium effects is huge. Or if you want, I have tried to explain this, what the polarization tensor of self-energy is. In part, is the big mass. So it becomes very massive. So not only that, because there is also the imaginary part of the self-energy, but essentially this suppresses the coupling. She suppresses the cross sections very much. So it's quite bad if you try to detect dark photon mediated scattering. Instead, Dirac semi-metals, they're called semi-metals because they have some characteristics of metals and some others that are not. These are engineered. You know, you can, condensed matter physicists can produce materials that never existed in nature. Graphene is one of them. It's a layer, monolayer. In any case, typical. And they are called Dirac because it has a quasi-particle excitation with a very, very small gap near the Fermi level that has a linear dispersion relation. Usually the dispersion relations are not linear unless they are very wavy. I will show a few. They are quadratic or more. They are not linear. But in this case, it is linear. Omega is proportional to k, which looks like a relativistic particle. For a relativistic particle, E is equal to P, right? In this case, the velocity is not exactly the velocity of light that is in the middle, but it's linear. And so it is a relativistic electron obeying Dirac's equation, and that's why the name Dirac materials or the Dirac semi-metals. And this is very good for a dark photon mediator because there are no large polarization tensors that are developed for those quasi particles. And I found this explanation maybe, you know, Dirac's equation, Dirac's equation is an analogy with QED. There is an extra gauge symmetry that protects the photon. Gauge symmetry protects the photon mass, right? Gauge bosons of exact apparent, not spontaneously broken gauge symmetries must be massless. Well, in this case, there is a sort of gauge symmetry that appears, an extra gauge symmetry that appears, and it protects the mass. So there are no strong medium polarization, large polarization tensor that appears. And so these materials are very good if you are trying to observe dark photon mediated interactions. And this is a picture that many people do. This is a usual, it looks like a light cone, but it's actually a picture of how they look in these excitations from the conduction band, the valence band and the conduction band. They practically touch, or they have very small gaps, and then you can jump from one to the other in these materials. This is the property. So here you have, for example, so this comes from Sensei Damik. You have these projections. And I put this plot, not because I'm going to show you these plots, because you have the experimental part that actually I bet show you much nicer plots and many more. But to say that here there is always this sigma E bar, and I would like to try to explain what this is sigma E bar that appears, you see. This is a reference cross-section that is always used in these plots in order to make your, so this is a halo dependent analysis, right? In which you assume that you put in a model for your halo, and then what you extract are limits in this mass, so cross-section, a particular reference cross-section that you extract from your problem as function of the mass, okay? And so let us see how this appears in many plots. So I have a two-way, yes?
A minor comment, I'm pretty sure that should be R&D not funded by DOE, the MNI, but they didn't get the DMNI. Maybe I'm wrong, there is something that is funded by the DMNI, but I'm pretty sure.
R&D.
Maybe I'm wrong, the R&D is separated from, they definitely didn't get the final DMNI fund.
Well, I don't know. This is older, and I think I may have. I think that they got something, because otherwise they wouldn't have. I don't know exactly. If the funding is terrible, so I thought. I'm coming from UCLA, right? $1 billion request from UCLA still is pending there. The faculty, actually, we had to sue the central administration in order of the university in order to know what were the terms of this negotiation. So it's quite. In any case, I think they got some money. But of course, you need always more. After a couple of a year or two, you need again more money, and I don't know. So it is not funded. Oscura?
DMNI was a project, was like this funding that 5 different experiments or something like that were vying for. The two that got it were Tesseract and LBMX, and Oscura, DM Radio, and ADMX. I want to say EFR did not get the funding. So maybe they got something initially, but definitely the final funding that they didn't.
They didn't get, yeah. But no, they finally they did. I mean, definitely they did have some money from the OE. This was funded, but who knows at what level? And then, of course, after a couple of years, you need again funding, and so this is not. All right, thank you for the. In any case, what I wanted to show you was this: the use of this sigma E. And so now I'm going to use the blackboard in order to go through this in an example. As I said, I tried doing it, and it took so long that I prefer to just write it down. Okay, so so when you have an atom and an electron. So the radial state, and I'm going to use simply hydrogen. It could be hydrogen. So this is a proton and an electron. And so if you see the density, the radial electron density probability, it is something like this with a long tail. But here, this radius is the Bohr radius. Bohr radius, which is 1 over alpha me. This is what I showed. And then this is here twice and 3 times and 4 and so on. So you see that you have many different. But the characteristic K, let me call this K as I use there, is about alpha me, and therefore the velocity or the initial velocity of the electron is about alpha. Okay. Now, this would be for ionization. For ionization, then in the end, K prime corresponds to a free electron. But actually, you may have an excitation. So let me use semiconductors. And there you have, well, you know, some complicated bands, but in any case, so this is the valence band, this is the conduction. And then electrons can jump, and this jump is of order of the band gap, as it's called. It starts at about 1 electron volt. Depends on, I think germanium silicon is about 1.3 electron volts, and something like that. This is the lowest and higher. So now let me mention, and in this case, therefore, here you have a wave function, an initial wave function. But in this case, you will have an initial wave function and a final wave function within the detector. Initial and final. This would be some function of K. This is some function of K prime. So I'm considering a scattering. And of course, in a scattering, you know, I told you the energy is about 10 to the minus 6, the mass. The momentum is 10 to the minus 3. So you see that for scattering, P0 is much smaller than P. And so whenever you have P mu, and I have been using all along, instead of having P square, this will be the full, you know, for momentum square. This is minus P square. So the same thing happens, therefore, with Q, right? So actually, that's why you use in all the propagators only the 3 momentum, right? For scattering. For absorption, it will be quite the opposite. For absorption, omega is the whole mass, and P is negligible. The 3 momentums. But in any case, we are at this point. So now the model of interaction that is used is a dark photon mediator. Let me call the dark photon mediator V. So now here, okay, dark photon mediator V. So here you have your dark matter particle. So here's a, no, I'm going to resolve this blob. This is V. This is chi of K prime, P prime. This is the electron. And then here you have your electron K prime. This should be all vectors. All vectors. Like this. Now, this coupling should be epsilon E, because the dark photon only, do you remember epsilon? This epsilon is the one that appears in F mu nu dark. This epsilon. And so you get in your mass eigenstates, you get another mixture of the interaction eigenstates. And this interaction, so the dark photon has a little component epsilon and of the usual photon, and through that couples here. Instead, I'm calling this G chi, whatever it is, it's coupled full. So now I can mention this is for a free, assuming that you have a free electron. Then you are, of course, you use your Feynman diagrams or whatever. It's and then you compute the spin average. Scattering amplitude. And it has this following form, let me call it this, but this would be for a free electron. Free electron square. This looks 16 G chi square epsilon E square. And then here there are a bunch of kinematic things. And here there is a propagator, Q square plus MV square. Okay, this is your amplitude for a free electron. If you would have a free electron, that would be it, but you don't. So now let us consider what happens with a bound electron. So bound initial, I mean, at least initial, bound initial electron could be, the final one could be free or not. Then what you get is something like this. This would be sigma. So here, there is a summation over possible initial states. There is this summation, actual integration. This is d3p prime over 2 pi cube. And this is d3 k prime. Okay, this is 2 pi cubes. I mean, we're going to care about the 2 pi's. Then here there is the delta of conservation only. This is the change in energy of the electron should be equal to the energy deposited. And you see that it is only conservation, only E conservation. Since the states that you are dealing with are not even against states of momentum. Momentum is not a good quantum number. It is violated. Oh my. Here it comes. I'm sorry, but I will have to continue here. I don't know very well this blackboard, otherwise I would have started somewhere else. Okay, the equation continues here. This is M free. But essentially, you will see not even all of it, M free square, but you take out this mass 16 pi, 16, not pi, M chi square, M e square. So essentially what you leave is the coupling constants of the propagator. No? Coupling constants of propagator square. And then this is what kills you. This is what actually is the serious problem of this, which is essentially this form factor, which gives you the overlap. So this J characterizes all your initial quantum numbers. And if it is free, then I'm going to assume that this is for ionization. Then your final state is well labeled by just the momentum. Otherwise, here you will have some other quantum numbers, and you have to sum accordingly. And this is a function of Q square. So this is the initial, and this is a good label only if the final electron is free. Final electron is free. So the equation goes all the way like this. Okay. All right. So what is this F? F. Here there are normalizations, you know. So I'm not going to write it well enough with normalizations and so on, because of volumes, you know, volumes, you have to put the square roots volume and things like that everywhere. But essentially, this is, except for some normalizations that I'm not taking care of, this is the overlap between the initial wave function and the final wave function, which could be also a plane wave in this case, so it could be something more complicated. For a free, it should be a plane wave. And here you have the plane wave that corresponds to, this is for the dark matter. The dark matter is always in a plane wave, it's a free particle. Okay. So if you would have a free electron, for a free electron, again, if I specialize for a free electron, then this is a another. These are all these phases. These are all plane waves, and then you put these plane waves, and what you get essentially is some normalization again, and the delta 3 of K. So in this case, for a free electron, J would just be the momentum. And then you will have a delta 3 of K minus K prime plus Q, which is what you would have then for the free momentum. But otherwise, it is not. Otherwise, this is complicated. And so now, move these equations up. So we have that equation there. All right, so now I'm going to take Q0. So namely, this is a reference momentum, the magnitude of the momentum. This reference in this business is always chosen to be this Q is ME. This is the reference value. And so we are going to write this coefficient that appears in the following manner, and this is where sigma appears. What people do is the following. You take M free, that in principle you can compute, this is really easy. You take out this 16 something, so essentially you leave only the coupling constants, m square. So you leave essentially gk square e epsilon e square over, and let me displace this. Here I will put Q square plus mv square square. And I will divide and multiply by Q0, replacing Q. So in this case, I'll have M E square plus MV square. All of this is a square. And here again, alpha ME square plus MV square square. Now, why did I do that? Because I will, there is an extra constant that is chosen to be put there, mu square. This is mu chi E square. So multiply both sides. This is the definition of sigma E bar. And here is the definition of what they call dark matter. This is, in this business, this is called dark matter form factor. It's a misnomer, but it comes just from the propagator. So this is called, in the literature here, I don't know why they chose that. Do you know why they chose this, by the way? This is not the correct, I don't know. It's not my choice. In any case, this is called dark matter form factor. But you see, it's not really, I mean, it's just a propagator. It's just a propagator. And it is done in this way. After some calculation, well, I will.
The reason why it's not called just a propagator is if you have weirder couplings like d mu.
Could be that it has more. But you know, it could be that you have other stuff. But in any case, it doesn't come from any really form factor, which is what you would have if you have extended dark matter. If you have extended dark matter, it will be
the actual correct name. I'm just explaining why it's not just propagator. There are other.
Yeah, it could be the coupling constants of the propagator. The name is confusing because sometimes you really do have form factors for dark matter. For example, you have cue balls or big objects. They interact also, they have substructure, and you may resolve the substructure. Okay, so this is the point. So in any case, yeah, well, this is the point now. Let me see. After some manipulation that I'm not going to address, after calculations, I would say calculations, you have this, that the cross-section essentially becomes this sigma E bar, an integral that finishes at a maximum energy, and this would be dE over this maximum energy and this dark matter factor square. Okay. So you can see that if the dark matter factor is 1, then sigma with this definition becomes sigma E. Now, I have only 2 more things. Where do I write? I mean, how these are sort of small, you know. Sorry. You have to know the blackboard to learn how to manage the blackboards, really. I'm accustomed to bigger, in any case, doesn't matter. Now, if you compute with a complete calculation, and this is shown in the lectures of Tongyan Lin, when you do something for ionization much more complete, summing over states and blah, 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 as function of K prime and Q, this is what you get. This function peaks at a value of K prime that is approximately the same as Q, and both of them approximately the same as Q0. All right. So in last instance, if when you are making all these simplifications and you're considering that all the scales are at Q0, you're not making a terrible mistake, because still you are representing where the maximum of this form factor would be. Now, you can see also the definition of the form factor. Okay. Returning to the definition of the form factor. I should have done it there, but in any case, what is the form factor of Q? Let me consider just the form factor. So you see that this is a ratio. I'm not going to, is that ratio without the squares? So when Q is alpha, all right. So what happens if MB is much larger than Q0 and Q? You see that the dominant value of Q is Q0. So when it is much larger, the denominator and numerator are both dominated by MV. So you get 1, right? So this goes to 1. And what happens in the other? This would be my definition, everybody does the same, of heavy mediator. Heavy mediator is that, one in which the propagator is just the mass, given by the mass of the mediator. Now, in the other limit, this will be the light mediator limit. You tell me what you get. You get alpha ME over Q. So essentially, you get Q0 over Q, magnitude of Q. And this is what is used in the calculation. Oh, I took F. Okay, if you want the square, then this will be.
The square is going like 1/54. No, right, like this is also.
This, if you take out the square, you get M square. Q square. No, you're right. Absolutely. It's like this. You were objecting. Thank you. Yes. Yes, my mistake. It's Q square. It's Q square over Q. And this is what is used in all the calculations, either one or the other. Right. No, this is not justifying any ways. It's that you, at the end, you use Q0 to extract something that is constant, a constant that makes sense, which in this case is sigma. So you extract sigma, the Q0 becomes something fixed to a characteristic value. And so now your sigma E bar is an indication of the couplings epsilon and G alpha that you have, right? Instead of being an indication of Q. So you extract this information. You pick up Q, a Q value that makes sense, and then alpha changes with the coupling constants, essentially, and the other parameters that are more relevant for the interaction. So this is what is shown. In particular, this is what is shown here, because these models are models of this type. These are models, there are two typical models. They have two benchmark models, one in which the mass of the mediator is bigger than the mass of the electron, 30 MeV. I mean, this is tabulated, mentioned many times. And another one in which is much lighter, is 10 to the minus something electron volts, or electron volt, or 10 to the minus something electron volt, or something like that. Okay. Oh, in the actual calculation, you have really to sum over all the possible initial states. And if it is ionization, huh? Yes, the free electron is the one that is the free electron amplitude enters into the calculation, and you essentially extract the sigma E from your free electron, because what you would like to get with sigma E is, as I said, information on epsilon and g chi. The Q0 is the value where this one is the typical Bohr radius. It is characteristic again.
It's just a normalization. You could have chosen to put one EV Q0.
It's just a choice. In fact, every time you see one of these plots, you should ask yourselves, what is that you're plotting, right? Because this, whatever is here, is an indication, gives you an indication of the strength of the interaction. But you can choose as a reference any point that you want, right? For example, if you change your Q0, you take, here you take Q0, right? Q0, but you take your Q0 to something different, it will be different. Of course, it will be related to this one through a known equation, because if you have to define it, you have to define what parameter you are plotting. Is that, okay. Sorry, how much I have? Ah, really not. Okay. Well, wherever we get, the rest will be in my lecture. Okay. So here it is. Now I'm going to go much faster because this was the easy. This is the completely impossible to understand unless you study the problem. Because really you have to start, you may start with these operators in which the operators are the same as I presented in dark matter nucleon interactions, but instead of the nucleon, now you have the electrons. Very non-transparent, but of course you will have an operator. Instead of having just a simple couple, you have an operator here, an operator there, that define what couplings you have. This is for the Hamiltonian. You start from this, from the Hamiltonian, and then you have to sandwich this between the incoming and outgoing electron, but of course you are not changing only the electron, you're changing your material. If this is, moreover, if this is not ionization, of course, as I said, you have to sum over all possible final states, and you have to, this form factor here, this F form factor gives you the overlap, and you have to sum over all the possible overlaps of the wave functions, initial and final. Okay, in any case. So in principle, you here can put any operators that you want. Usually, for a dark photon, this is called GD. This is the dark matter, I call it G chi here, but it's the same parameter. And you see that actually this CL becomes just the propagator and the coupling constants. This is what it is, just for that. Where this epsilon is the parameter in the mixing, in the kinetic mixing, and GD the coupling. Okay, then you continue and you define, with respect to this Hamiltonian, then you define the number of events. You start from Fermi's golden rule. Fermi golden rules is Feynman diagrams. You assume right conservation of p mu. Here you are assuming conservation of energy only. You have conservation of energy. Yes. Yeah. Yes. This is a way of summing over all things that are not zero. Yes. This is a general form of all of this. Afterwards, you have to take all the complications, all the amazing complications of all this. Because, of course, here, all of these issues happen in a material. And finally, at some point, you have to have the material represented. Here, the material is represented by this factor, which is the dynamic structure factor. defined in general in this way, which is borrowed from condensed matter. All of this is borrowed from condensed matter. It's new for particle physics, but all of these techniques are borrowed. The only thing is that they are, I mean, particle physicists are not condensed matter physicists for a good reason. It's a different type of, it's very different. So to master all the techniques to make the connection, the language is different. It's the same as particle physics and nuclear physics, believe it or not. You have really, you're at the boundary, but very different languages. And so it's quite laborious. So that's why I wanted something that was relatively simple. In any case, now, for the simple case of at rest, you get a delta function here, but otherwise you don't. Okay, let us continue. Phonons in crystals. I had a small presentation. I think I will just post it together at the end of my lectures. I have some notes in which you can start with phonons just by having something that you may have solved for in physics 1 or your equivalent, which is lightly coupled oscillators. You may start actually with something, and Tongyan Lin has this. So okay, if you start like this, you know, point-like masses, this is a model of a solid, a linear model of a solid. And here you have the spring constant is K. And then you go to the continuum, you have a model of a solid, and you see appearing, instead of having, so this would be the displacement you call U sub I. So when you go to the continuum limit, continuum, then this V sub I becomes a field, and then you have essentially this is the field of phonons. This is the field of acoustic phonons. In acoustic phonons, if you see these little arrows, all the atoms move in the same manner, in phase. In optical phonons, they move in different phases, out of phase. The acoustic phonons are gapless, namely they get to 0 here. The optical ones are gapped, and they correspond, therefore, to they have different dispersion relations. This one here has, again, it's just omega. This is omega, by the way. I think I cut the, but this is omega. This is the energy, and this is K. So omega is proportional to K, and by something that is the speed of sound, because these are pressure waves, essentially. In 3 dimensions, you have longitudinal pressure waves, transversal pressure waves, and you have things that are more complicated where the atoms are at, and they have higher energy. Yeah? So this is approximately constant. Okay, and you can use both of them. You could excite both of them. You see a scattering of phonons in polar material. Polar materials are those in which the material naturally have a dipole, a charge. It's more positive on one side and negative on the other. So they are little dipoles, and they are very good to couple to dark matter that has magnetic dipole coupling, actually. In any case, you see this LA, this A is for acoustic, L longitudinal or transversal, and longitudinal transversal. The ones that have been studied are these. I'm not sure I can even pronounce all these names. I think this is gallium arsenide, is that correct? And this thing is, who knows, but it's sapphire. It's aluminum, some oxide, yeah, sapphire. But it would be otherwise some aluminum oxide or some way or the other. In any case, you can see that your life becomes very complicated, right? It's not, in any case. these materials are extremely anisotropic. And this gives an advantage because the energy would depend very much on the incoming direction of the WIMPs, and you would have a daily modulation, a strong daily modulation of the signal. Now, the scattering of phonons, this is actually some scattering of phonons of SI scattering. Again, this has SI. This S you can write, and if you want, you go to Jure's review. To me, I didn't write them down because they are very non-transparent. They are all functions, right? For the non-initiated, they are just functions. Now, so they are presented, all of these functions, right? But what's the meaning of these functions? You have really to work at that because I don't have any separate way. Now, you can excite also other things like magnons. Magnons are spin waves. And for that, you need a coupling with the spins. So magnetic dipole or anapole or pseudoscalar mediated dark matter that couple to the spin. These are some of the couplings that I mentioned at the beginning, right? And then you can have, I don't even know what this is. Yes, YIG. Yttrium something. The Y is yttrium, but that's as far as I can get. YIG. I don't know. It's yttrium something or the other, in any case. In any case, as I said, I'm not in any case, so you see that many things that actually justify, therefore, a multi-target proposal. You can see how many different things you can address. And if you can address more than one in a detector, better it is, right? So there are so many. Okay, I want to say a few more things, and let us see how many I get to. Wherever you can measure or get a limit through a scattering on a mass, then you can get the same limit on a dark matter particle that would be absorbed with a mass that is 10 to the minus 6 of the initial mass. Because here you are giving the kinetic energy in scattering, and the kinetic energy is 10 to the minus 6 times the mass. Assume instead a dark matter particle that gives all its mass, it disappears. You see, for that, you have to have dark matter that actually couples in this way, right? Standard model, dark matter particle goes into another standard model. Okay, this three particle vertex must be there, all right? So if you can get to 1 keV in mass through a scattering, you can get equally well to 1 milli-electron volt in absorption. Dark photons are absorbed, right? You can have a dark photon like this, dark photon, and electron. This is epsilon E. So dark photons, checked. They are good candidates. Another candidate that you're going to see next time are axions. And I wanted to mention, there are field theory actions, there are string theory actions. These are usually called ALPS. And these axions are actually pseudo-Goston bosons, and those appear in a different manner, but they interact in the same way. And well, axions started coupled to actually QCD, and they're pseudo-Goldstone bosons, namely when you have a U1, the U1 Pichet queen assumed, an extra U1, global U1. When it is spontaneously broken, then you have this a particular type of inverted Mexican hat or bottom of a bottle of wine, a type of potential energy. And wherever you go, the spontaneous symmetry breaking means that your state is in one of these points along the orbit of minima, and the perpendicular direction along the orbit of minima has zero mass. This is the Goldstone boson. The Goldstone boson is not exact when the symmetry is not exact. In this case, in none of the examples that one has in model building, these are exact symmetries, and so the orbit of minima is slightly tilted, deformed, and therefore there is a little curvature. That curvature is the mass. But the essential point, so there are axions, and there are axion-like particles in which the coupling and the mass are parameters, free parameters. But you have couplings that are all of this type. So this is the traditional axion coupled with gluons, but there is also the axion coupled with photons, the axion coupled to two fermions. So you have this coupling that allows axions the same way as dark photons to be absorbed. So they are measured in there, they would be searched for an absorption. Here there are a few more things. I mentioned the Migdal effect. The Migdal effect is for coupling with, so this is a collision with a nucleus. The nucleus is given, imparted some energy, recoils, but in this case there is an excitation of the cloud of electrons around, and followed by a de-excitation emitting, kicking out essentially an electron, or it could be a photon. This was studied in 1939 by Mr. A.B. Migdal, and actually he computed the already quite well semi-classical formulation, the cross-section, and so on so forth. Now, assuming as it is correct that most of the energy would go into the nucleus and a little bit into the electron, then you can factorize the two things in when you are computing your interaction rate. And here you have that for the atomic Migdal, because it can happen also in crystals actually. But for atomic Migdal, when it happens to just one atom, the ratio between just ionization and the Migdal effect is like this. You see, depends on Q. So actually, Migdal spectrum is dominated by large Q values than ionization. It has a typical spectrum. As I said, it was looked for. Here it is, the paper 2307 and so on. You commented about it, that actually.
Your because apparently they presented that they finally think they may have found
in their data.
Yes. By Newtons. No, by who? I think the model correlation. So yeah, unfortunately, so I was not myself on one of the courses of the presentation of the
Well, in any event, I'm mentioning this because I have just two more slides, so just in time. So two more slides. Huh? No, I mean, we can discuss as much as you want, but very brief. In any case, I don't have anything more intelligent to say, except for the fact that this would be important for lighter matter, because actually, you know, it's a good charge deposition is, you know, if you can see the charge deposition, that would be another handle on these light things. Okay, so two more things. Something else that is important, although it's a small, but a small effect, but in any case, you expect some dark matter to be boosted. Namely, what does it mean? That it would have higher velocities than what corresponds to the halo, dark halo. And this is because this has been analyzed since several years, many years ago. In any case, again, please go to Jure's review for the many reference about this. But in any case, this is one of the first Kuvaris in 2015. Okay, in any case, you can have multiple scatterings within the sun that accelerate a particle, and afterwards it goes out. It doesn't lose enough energy to be bound to the sun. On the contrary, it may gain, and so it escapes. Collisions with cosmic rays, evaporation of PBH at present, those that tend to the 10 gram, whatever it is, that they will be evaporating. Decays or annihilation of heavier dark matter, even if the heavier dark matter is still around, it may actually decay a little bit, and so on. You may have a little bit. This is just for a small fraction, but even a small fraction could help you put some of this dark matter above threshold. And these are some, this is a compilation that comes from my favorite review. Actually, Juris, it is a compilation. They have very nice compilation, actually, of data. Actually, they did quite a good job at that. And then this is my last thing. You can do a halo-independent analysis of in the same way I mentioned before. The kinematics is more complicated, but still, we use V mean as independent variable, and instead of the momentum transfer. The momentum transfer has, in general, this is for spin independent coupling and so on. So, but in any case, you have to be careful about the Jacobians or the transformations. But we change the order of integration. We put it as an integral in this way, with a kernel that depends on your particle characteristics and detector, and this function eta, which depends only on the halo. And what we computed using all this machinery actually was these kernels. These kernels act as window functions through which measurement of the rate can give you information on this eta function in a certain range. And here you have for particular, this is an example for 100 MeV mass in xenon, when the form factor is 1 over q squared, or when the form factor is 1. And you have the different energy depositions, E prime. E prime is what you measure, energy deposited. And this is 30, 15, and so on. Here you see where these window functions are non-zero. This is where xenon, if they would observe something and the mass of the particle is 100 electron volts, they could tell you something about V mean. So the lower your threshold, the more about V mean at lower speeds you can say, right? So here you have that in this case, in the case for, so it's always 1 over q squared. In any case, this is something, in any case, in this example, you can see actually that you can get, these functions are not zero, even up to 200. But you have no information below 200 here, no information below 400 here. Now, yes, then I'm done. I'm done. I'm sorry. So if you have questions, please, yeah. There are 3. You have to order.
Interaction with solid stuff. Are we treating this because today we're only focused on like condensed matter based the detectors, or is it just that like pretty much all detectors?
Well, this is something that experimentalists, not me, have to contend with in order to interpret what goes on inside their detectors. If you have a silicon-based, germanium-based, all of these things, phonon materials and so on, you have to understand. But from the standpoint of theory, you can get away without knowing, just using their data processed. However, in this case, in this lecture, this is essential for the interaction, not for the measurement, not for the characteristic of the detector, not for E prime versus ER, but just to couple. Okay, and then the coupling has these properties inside. You cannot even compute what is your cross section in the material because you are using bound electrons, or you're using phonons or magnons. I must have jumped. I mentioned helium, proton, something. Yeah. She collaborates with theorists in particle physics, like the carbon cathena, for example, they calculated if you have light dark matter scattering on xenon, like what's the difference if you go from the free electrons to the liquid phase, right? The good, I mean, they have a nice paper on this. The good news is it's not a huge difference, and they also give kind of a recipe how to translate from, from the free electron approximation, which is often not the correct one, to the liquid phase. I'm just saying. Yeah, this is for xenon, but you have to do it for all. You have to. Right. Yeah. Yeah, you have to collaborate with in order to do this well. But in this case, it's different because it's not that you have a recoil of a nucleus and then you have to see what this nucleus does, which does a lot of things inside the detector. Is that in this case, in order to understand how it is coupled, you need the materials. Okay, this function, this thing. Yes, there was another question. The back, and then the back.
People have done this final stage. It's just then it's.
Yes, you have to sum. No, this was the Mickey Mouse, right? Example. This was simple, but you have to sum over everything that need to be summed. Like always, you sum over all initial states, average over all initial states, sum over all final states. That will give you the same type of process. In this case, you characterize it with Q, and the momentum transfer is what you would see, right?
So even the same final state is not entirely accurate. It is unbound, but technically you should be accounting. There's also a wave function that is non-trivial close to the origin.
That is true.
Right, so
that is true.
Similar thing.
This is the Mickey Mouse calculation, right? Yes. Now, physicists always have these Mickey Mouse calculations. They do it. The issue is that I needed to find one that was available because, this. But you always do this approximation just to know if the order of magnitudes are correct. Because if you fail in an approximation that is simple but not, sort of correct, you fail by 10 orders of magnitude. Forget the idea. Even if you do a good calculation, you're not going to gain 10 orders of magnitude, right? So this is the same here. It's just did it answer your question? Sorry? Magnons. Huh. I have no. I think they're both. They should be bosons.
So yeah, they're both. They're built on a vacuum which is not trivial because it is actually fermionic, but they are bosonic excitation on top of this fermionic.
So they are spin waves, but how do you describe these waves is really complicated. I show you this, and why it is using gig, I have no idea either. This depends.
I think Yig is considered very good because it's a if I remember correctly, it's a ferromagnet and it can have a very high Q factor. You can make it very precisely and basically get the spin wave to live for a very long time. While other ferromagnets tend to have imperfections that are hard, I think, to get rid of in the fabrication stage. I forget the part, I know. but it's both very high density, so they have large spin density, as well as this long lifetime. The Quarks collaboration, I think, has purchased kind of the highest quality view the world required. I remember from before that.
There are others, moreover. There are others that they then rotons, and in helium, in superfluid helium. Yeah, but in any case, there are others in well, superhelium, but in superfluid helium, they were in the 80s trying to measure things with rotons. So I'm not. Yeah, I'm not sure where they are, but this idea had, it has all these ideas, of course, are not entirely new. They were already in the 70s and 80s. People thought about various different things, but never in that with this intensity. Yes, sorry.
I get an actual question. The neutrino, so the solar between the cross section.
Ha, yes. The,
I thought that maybe a while ago you told me that you were calculating it. Did that
it's
Misunderstood.
I we were thinking of
yeah, sure. You need to do the same thing with neutrinos. You need to do the same thing with neutrinos. No, it's not easy at all, isn't it?
No, but I'm serious, right?
Yeah, no, I think that there is a problem, a background, really, until you build a detector. That's why you have been, what, 30, 40 years building a detector, because you have found all the backgrounds. Though you don't have I believe you. These backgrounds need to be, it's not the background? You want to study a neutrino signal. Well, nice. What is a background for somebody is a signal from for somebody else. That would be great. That's always so. The cross sections. No, I can imagine that this would be very complicated.
So maybe.
In any case, I don't think I have anything to add at this point, but there are many, many things to do. There is an enormous amount of work to be done. Okay, that's it.